We would like now to give an analog of the Green's formula for surfaces that do not lie on a plane but are in 3D. So imagine that in a 3D domain, we have a surface, and let's call it S, and it has a boundary. And now we have a vector field, which is defined in that 3D domain, and obviously it's defined on the surface and its boundary. And the truth again is that it needs to be defined just on the surface and its boundary. The trick here is that since we are in 3D space and we would like to have an analog of the of Green's theorem, and in Green's theorem, we specifically have a vector line integral that has the counterclockwise that is on the boundary of the domain, and it has the counterclockwise orientation. The boundary does. Here, there's nothing in 3D space like clockwise or counterclockwise. I mean, think about it. If you have a clock and it turns one way that you think of it as clockwise, and go behind it, and all of a sudden the clockwise is counterclockwise to you. So what we do, however, is we can define when the orientation of the surface and its boundary can be associated with each other, can be compatible, as we're going to say. So remember that the surface is oriented by means of the choice of a normal vector. The boundary, on the other hand, is oriented by the direction in which it is traversed. So our agreement is that for the purposes of generalizing Green's formula in non-spatial, actually non-planar domains, what we're going to do is choose a normal vector and then make sure that the orientation on the boundary is chosen as follows. If you followed that normal vector all the way to the boundary and you stood on the boundary in the direction given by the normal vector, then the domain should be on your right hand if you faced the orientation that was chosen on the boundary. In this picture that I have right here, the correct orientation would have been this way, because I have chosen what seems to be upward for this surface. If I stand upward on that surface on the boundary, then the orientation that I have to face on the boundary so that the domain is on my left hand is precisely the one that I chose right here. So we're going to talk about compatible orientations of the surface and its boundary. And if this is the case, then the Green-Stokes formula says the following. That the vector line integral of the vector field F around the boundary of the surface, where now the boundary has been oriented in the way that we have indicated, is going to be equal to the vector surface integral of the curl of the vector field through the surface, where now the surface has been oriented also in the way that we have indicated. Please understand that we can express this in two different ways because there will be another pair of compatible orientations. If you think about it, the boundary can be oriented in two ways. The surface can also be oriented in two ways. We suppose that we have an orientable surface. We're not doing this over a non-orientable surface such as the Möbius strip. So we suppose we have an orientable surface, and the surface has two orientations, the boundary has two orientations. So there are four different ways of combining those orientations. Out of those four different ways, two of them fall within the description of this theorem, so are compatible with this theorem. And two of them do not fall. So for this theorem, so this formula would not be correct. It would not be too wrong. The two sides would just be opposite to each other. Okay, so in a more general way, you could say, you know what, if I compute the vector line integral on the left, the vector surface integral on the right, and I choose two random orientations for for the boundary of my surface and for the surface itself. Again, for the boundary of the surface, it's the way in which you traverse. That's what the orientation is. For the surface itself, it's a choice of a normal vector. If I do that, and I don't pay attention to how these orientations are chosen, then the two integrals will either be equal or they will be opposites of each other. Right? But in this case, what we're saying is that if you take care of the orientations and you choose them in a way that they're compatible to each other in the empirical sense that we explained, then the two integrals are going to be the same. And this is Green-Stokes formula. And if your domain happened to be a domain on the plane and you try to apply this, guess what you would obtain? You would obtain the Green's theorem. Okay, so how do we use this? Again, this is a translation theorem. It translates one integral into another, and it could be used in two different ways. But the example that we're going to see is going to go this way. Okay, so we're going to use this formula in order to compute a vector line integral by expressing it in terms of a vector surface integral. As you might expect, such an example will be quite labor intensive because we will have to compute so many things. So let's get on with it. And so use the Green-Stokes formula in order to compute the integral y squared dx plus x plus z dy minus xy squared dz on the boundary of S, where S is the triangle with vertices 1, 0, 0, 0, 2, 0, 0, 0, 1, oriented in the way shown below. Let's draw it, even though we could have indicated from what vertex to what vertex we go. So let's say this is 1, 0, 0. 0 to 0 must look a little larger, and then we have this. So this is our triangle. And let's say that we want to orient it this way. So it's oriented this way. So this is again the point 1, 0, 0. This is 0, 2, 0. And this is 0, 0, 1. So now, if we orient the triangle this way, the question is, what is the correct orientation on the surface of the triangle? And you just need to picture yourself sitting on the boundary and try to figure out what way should you be sitting so that the domain is on your left hand when you're facing the boundary in the orientation that is indicated here. And a little experimentation will show you that it's pretty much the upward way that you should be sitting. So the surface of the triangle needs to be oriented with the upward normal. Okay, so what is the underlying vector field? The underlying vector field is f of x, y, z equal to y squared x plus z minus xy squared. And its curl will be given by what? I mean, remember that it's the curl that we need to integrate to find the flux integral for the curve. And it's going to be the gradient operator cross with f, which is I, j, k, partial differentiation with respect to x, partial differentiation with respect to y, partial differentiation with respect to z. And now we will have y squared x plus z minus xy squared. So now delete the first row, delete the first column. What will you get on the first component? So you will have minus 2xy minus 1. And on the second component, you will have minus y squared. And since it's the second component, we will make it y squared. And in the third component, you will have 1 minus 2y. So that's the curl. And now we need to find the parameterization. We have solved a problem like this before. So what is a good parameterization here? We could just take the graph parameterization. After all, this is what plane? It's x plus y over 2 plus z is equal to 1, right? So you can always solve for z in order to think of it as the graph of a function of x and y. So, and the domain will be the projection of this onto the xy plane. Here, I'm going to think of it as the uv plane. So here's the u-axis, here's the v-axis. This should be the point 2, this should be the point 1. So this is u plus v over 2 is equal to 1. And d is going to be the domain of all uv's, such that, let's do horizontal integration here first. So u is going to be between 0 and 1 minus v over 2. And what is the vertical range of all this? That would be for v between 0 and 2. And of course, we should write explicitly our parameterization, which is a graph parameterization, u comma v comma 1 minus u minus v over 2. Okay, so let's pull back now the curl to the domain of this parameterization. So that means what? That we should take the oops, sorry, wrong tool. Let's see if I can erase this. Yeah. Okay. So we should take this and replace x by u, y by v, and z by 1 minus u minus v over 2. In which formula? In this formula. So this will give you minus 2uv minus 1, v squared, and 1 minus 2v. So this is the pullback, and we need to compute the normal vector. And the normal vector should be constant because everything is linear here. So we will have the cross product of g sub u cross g sub v, which is 1, 0, negative 1, across with 0, 1, negative 1/2. How do I find this? How did I find these two vectors? By just taking the partial derivatives for g, first with respect to u in its 3 components, then with respect to v. So here I will have 1, 0, negative 1, and 0, 1, negative 1/2. And this will be what? It will be 1, and the middle one will be 1/2, and the last one will be 1. What is important to see here is that the last coordinate is positive, which means that this is compatible with the orientation that has been chosen on the surface, because we said that on the surface we choose the upward orientation. So finally, what we need to do is take the dot product of the pullback of the curl on the domain of the parameterization and the normal vector. So this will be minus 2uv minus 1 v squared 1 minus 2v dot with 1, 1/2, 1. and this will give us minus 2uv minus 1 plus v squared over 2 plus 1 minus 2v. It's not like we have an awful amount of cancellations, but we get v squared minus 2uv minus 2v. Okay, and we need to eventually, so finally we found what we need to integrate, and where does it need to be integrated? It needs to be integrated here. Okay, let's take a deep breath and do this integration. So it will be the integral of v squared over 2 minus 2v minus 2uv on that domain that we call D. And how is integration done in V? We start with respect to u from 0 to 1 minus v over 2. And then it's dv from 0 to 2. And we have v squared over 2 minus 2v minus 2uv. So this will be integral from 0 to 2. Let's take the antiderivative with respect to u. So this will be uv squared over 2 minus 2uv minus u squared times v. And we want to go from 0 to 1 minus v over 2 dv. I mean, we have to finish the work. So let's do it. So we will have 1 minus v over 2, the whole thing over 2 times v squared minus 2 and oops, yeah, okay, we're good. So 2 times 1 minus v over 2 times v minus 1 minus v over 2 squared times v dv. Let's multiply out. So what do we have? We have integral from 0 to 2 of v squared over 2 minus v cubed over 4 minus 2 plus v minus v plus v squared minus v cubed over 3. Not over 3, over 4. And let's take the antiderivatives now. So it will be v cubed over 6 minus v to the 4th over 16 minus 2 v plus v squared. Actually, this thing cancels with that, so we don't need it. So I'm going to jump directly to this. V cubed over 3 minus v to the 4th over 16. And we want to go from 0 to 2. Again, it is possible that here I have made some numerical error, but this is the idea of this computation. So if you put, if you set 2 now, you will get 8 over 6, which is the same thing as 4 over 3 for the first term. For the second term, it simply becomes minus 1. For the third term, it's minus 4. Then you have an 8 over 3. And finally, you have another negative 1. So how much is this? 4 over 3 plus 8 over 3 is 12 over 3, which is 4. And then you have minus 1, minus 4, minus 1. These two things cancel, and the final answer is a negative 2, at least according to this computation. Like I said, I haven't double checked it, so Please forgive any error that has been committed here, but certainly the most important part of this computation is all the preparation that went into it, which is all these interpretations right here. And that completes our example on the Green-Stokes formula. Thanks for watching.